Hey there! Welcome back. This is the 5th lecture of the Fundamentals of Electrical and Computer Engineering. We are this time looking at special cases of node and mesh analysis, which includes supernode and supermesh. And we'll get into what that actually means when we go through the things. So, previously we have seen node analysis and how it comes from Kirchhoff's current law, and that we use it to find the voltages in a circuit, right? And mesh analysis comes then from Kirchhoff's voltage law, and we use it to find the currents around a circuit. Now, sometimes it's advantageous to combine resistors to find an equivalent impedance source. And sometimes we need to convert sources to make our lives easier. So all of these things are really important tools that let us do the math of circuits so that we can understand what the circuit is telling us. And part of that is recognizing some special cases of node and mesh analysis. So, let's look at this circuit here. This one here has a current source on a branch all of its own. It has a battery as its voltage source, which isn't super important, but recognizing the battery sign is important, and recognizing that the long end is the positive side, that one is also important. There's something up with this. If we wanted to apply mesh analysis to it, we would have a really bad time. We can't apply mesh analysis. And it's because of this current source. Now, it's not because there's a current source in it at all. It's because that current source is on a branch all of its own. Basically, if you were to make a loop here, that loop would have to be IS, right? I source. Except that the math won't come out that way. If you were to just apply mesh analysis the way we've learned how to do it with three loop currents that we then had to use a series of equations to solve for, we would end up with something that says no solution. Because we would end up with some answer from our solutions equals then would have to equal IS, and it doesn't. So in these cases, we cannot apply mesh analysis. We'd have to try something else. Let's look at this circuit now. We got a battery, but we've also got a voltage source. And that voltage source is on a branch of its own. This one we cannot apply node analysis to, and that has to do with our assumptions. So we can't apply node analysis because the only node is connected to an ideal source. And we know that logically, we know that there's current in this branch, but an ideal source has zero internal impedance. So we're kind of stuck. We can find the current here, and we can probably find the current here as an equation, but we can't actually get a value using Ohm's law here. So this is why we need to know both mesh and node techniques, because when we're looking at super nodes and super meshes, we'll end up having to apply both of them. Also, if one is inapplicable, we probably can apply the other one. If you were to apply mesh analysis, you'd probably succeed. If you were to apply node analysis here, you would succeed. But we have to understand the limitations of both tools. So let's look at supernodes. So supernode analysis deals with a supernode. What a supernode is when there is a voltage source connected to two node voltages. So we are looking here. This spot here. And I'm not sure that's super visible. So let's use a lighter color. Let's use this one. There we go. So we have this A, we have this B, and we have this voltage between them. Well, we know, because this is what node analysis teaches us, is that there's a voltage here, there's a VA here, and there's a VB here, but they are somehow connected to this source without being only that source. And I know that's a little bit to unpack. So let's just go through it. So to get through this, we have to apply both node and mesh analysis. So why is supernode an issue? So we can't know the current through the source because of the ideal assumption. Basically, since we decided that we're going to take all sources as being without resistance on the inside, they can provide whatever the heck they want, but we can't apply Ohm's law to it. So that means we can't just use a different method, right? We can't just then use mesh analysis, because A and B have unique voltages. Due to the other devices and the battery. So essentially, you've got three voltages attached together in a weird way we have to figure out. And it's because they interact differently in this situation that we have to apply a special technique. That's why we have to use supernode analysis. So let's just try and figure it out, okay? So the first thing we have to do is identify the supernodes. And we did, right? It's here. It's going to be A, and this battery, and B. And this is V battery. Right, capital B is for battery. Alright, so the next thing is we need to look at just the node, as if it was a circuit of its own. And from that, we'll get a KVL equation. So we're going to say A, and then the battery, like that, there we go, and B, and this is V bat, right? And then we're gonna say, because we know that there's a voltage at A, there's going to be plus minus VA. And same here, right? There's a unique voltage at B, so we're going to get plus VB minus, and we're going to connect it like it's a circuit. We're just going to pretend this is a circuit. And we're going to draw our current, right? So we'll get a KVL equation. It'll be 0 equals, all right, we're coming into the positive side, so V battery, plus, because we're coming into the positive side, of VB, and then we're coming into the negative side, so minus VA. Excellent. First equation down. We have several unknowns, so we have to find more than one equation, right? So where are we going to get that? We are now going to look at the whole circuit. the whole circuit as if the supernode were one point. And then we're going to find a KCl equation. So instead of this, we're going to say that we've got, all right, let's just redraw the circuit. So we've got some Z1, and then it connects to the supernode, right? And at that, it connects to this Z2. And there's a ground down here. And we've got, all right, we've got one parallel resistor and two parallel resistors. And we know that when there's blank wire, it's all one node. So this is all the supernode. So let's figure out all the stuff going into the supernode. So we've got, well, let's just draw it as one single node. Sure. We're going to have some current I1. Then we're going to have some current I2. Then we're going to have some current I3. And then we're going to have some current I4. And so we're going to have our KCl equation. We're going to have 0 equals I1 minus I2 minus I3 minus I4. Right? Easy peasy. And we're going to, let's make a note. This is from an old version of the lecture. Please ignore that. So if it is possible for these kinds of circuits to have regular nodes and supernodes. If there was another node that was just like a resistor here, and you had a point here, this would be a node. It would be a node that would be difficult to get at because this is a voltage source, but either way, you can, if there are nodes that are not part of the supernode, do not include them in the supernode equation. Unless, you know, they're share a current. But like there are multiple steps. So let's keep going. Let's keep going. So after that, we'll address any regular nodes, right? This circuit doesn't have any. This circuit doesn't have any. But if it did, you'd write a KCl equation for each and every one of those. So next up, we're going to put it together and we're going to solve for it. So we have two equations, right? We have this V battery plus VB minus VA, right? From our KVL. So we're going to go ahead and write that down. VB minus V little b, plus V little b minus VA, right? And then the second one is up here. It's our KCl equation, and it's going to be I1 minus I2 minus I3 minus I4. So let's say we have these values. Let's say we've got these values. We've got 6-volt battery, we've got a 14-volt source, we've got a 4-ohm Z1, we've got a 3-ohm Z2, we've got a 2-ohm Z3, and a 6-ohm Z4. Alright? So let's just plug everything in. Equation 1, V battery is 6 plus VB. Okay, cool. Well, we don't know that one, so we're going to leave it a variable. Minus VA, again, we don't know that one, so we're going to leave it a variable. Next, equation 2, I1. Well, we don't know them per se, but we can probably get it in an Ohm's law form. So let's write it as 14 minus VA over 4 minus VA over 3 minus VB over 2 minus VB over 6. So notice how these are written as they come out of the nodes they come out of, but we wrote them all in the same equation like it's one big node. That's kind of the critical point here. So if we then kind of solve these out, we're going to get 6 equals VA minus VB. We're going to get, let's see here, 14 over 4 equals VA times 1/4 plus 1/3 plus VB times 1/2 plus 1/6. Okay. So I just grouped the fractions so that we didn't have to go through all of that right now. All right, and that gives us 5.6 volts for VB and minus 0.4 volts for VA. So notice how neither of those is 6 volts. All right, so either of these turning out negative just means that we assumed a direction that's opposite what the actual direction is. So it's okay. It's okay for this to become negative. We know that the principle is correct. So if that's supernode, let's look at supermesh. So supermesh is when a current source exists between two valid current loops. What do I mean by that? Well, if I were to draw loops for all of these, here's I1 and I2 and I3, and well, okay, there's a current source between I1 and I2, so we're gonna have to figure out what to do here. And hint, just like supermesh or supernode, supermesh requires us to apply both node and mesh analysis. So, first of all, let's figure out why supermesh is an issue. We know that device currents derive from the loops touching them, right? But the current source affects those loop currents too. So we can't just use node analysis because we assume ideal sources. So we can't just look here and try and find all of the currents and voltages because the ideal source, they have zero impedance. And so we can't get a current from a voltage source. And yes, potentially could convert the voltage source if there had been a resistor here in series. But since there's not, we can't convert this source. So we are stuck using the supermesh analysis method. So let's go through it. First off, we need to identify the supermesh. And it's going to be this entire box, okay? This weird dog leg. It's going to be the source all the way over to Z1, down across Z2. Oops, hold on. Down across Z3, and back up to the source. And note that we have disregarded the current source when we redrew this. We'll come back to it, I promise. So, next up, we are going to look at just the supermesh as if it were continuous. and then we're going to write a KVL equation for it. So, oops. Just like before, we got resistor 1, we got resistor 2, we got resistor 3, and I forgot to draw the source there. We got a source. Specifically, the voltage source. So, with that, let's say we've got some current and we're going to follow it around. And we're going to say, we're just going to do these in terms of their voltages right now. So we're coming in to the positive side of device 1, so we're going to have V1. Then we're coming into the negative side of device 2, so it's going to be minus V2. And then this one's super weird because it feels like you have to follow this thing around. So it's okay to just draw individual curving arrows to figure out what direction you're coming into. We're coming into the positive side of of device 3, so we're going to have plus V3. And then we're coming into the negative side of the source, so minus Vs. And that's equation 1. Next up, we're gonna label all the meshes as if we're applying mesh analysis, just for regulars, right? So we're gonna have I1, I2, and I3. Even though we know that this is kind of a fresh mess, right? So notice how the IS branch only touches currents I1 and I2. So that we're going to need to recognize for later. So we are now going to find a node that touches I1 and I2 passing through it. So basically we're going to find a node here where we can say that the branch currents are these loop currents. And then we're going to write a KCL equation for it. And I'm going to choose this node. This one here. It touches our source, which we need, and it relates I1 to I2, which is what we need. So if we draw it out, just following the current loops, we've got I1 in on this side, I1. We've got I2 out on this side, I2. And we've got this I source coming in, I source. So our KCL equation is going to look like I1 plus I source minus I2. Sweet. So now we're going to address any regular meshes with KVL. And there's only one regular mesh here. It's the I3 mesh. I3. So we're just going to write it out. So we have positive into Z2, so plus V2, right? Into the positive side of Z4, so plus V4. Then we are going into the negative side of the source, so minus V source 2, just to denote it from the other one. And then we're going to have into the negative side of Z3, so minus V3. And that's our equation. Next thing, we're just going to put it all together and we're going to solve it. So, same as normal, we're going to find the Ohm's law equivalents of any of these that we can, and then we'll chuck it all together. So, equation 1 was IV source plus Z1 I2 minus Z2 I3 minus I2 plus Z3 I1 minus I3. All right, equation 2 is going to be minus V source 2 minus Z3 times I1 minus I3 plus Z2 times I3 minus I2 plus Z4 I3. And then finally, we have I1 plus I source minus I2, which came from our node equation, right? So let's say we have these values. Let's say that this source is 400 volts, this current source is 4 amps, resistor 1 is 100 ohms, resistor 2 is 50 ohms, resistor 3 is also 50 ohms. This voltage source down here is 50 volts, and resistor 4 is 100 ohms. Let's just rewrite the equations. So we're going to have minus 400, right? Because that's our source. Minus 400 plus 100 times I2 minus 50 times... Oops, that's supposed to be a 50, not 5. 50 times I3 minus I2 plus 50 times I1 minus I3. And if we kind of simplify that out a little bit, we're going to get 400 equals 50 I1 plus 150 I2 minus 100 I3. All right? I'm going to scroll up a little bit. So equation 2, right? So we're going to have minus 50 minus Z3 is 50 times I1 minus I3. I'm not going to have enough room. Plus Z2 is 50 times I3 minus I2. Then plus 100 I3. Yeah, that's everything. So if we simplify that one down, we're going to get 50 equals minus 50 I1 minus 50 I2 plus 200 I3. And then finally our current equation, which is not going to change a whole lot, right? We just have a value for I source, which is 4 amps. And then we're going to have I2. And we're going to go ahead and get this in terms of I1 because it'll just be fast. Basically, just solve this for one of them. So I1 equals I2 minus 4. Yes, that's correct. So if we do all of the algebra to get through this, or plug it into a solver, we're going to get I1 equals minus 1.5 amps, I2 equals 3.5 amps, and I3 equals 1 amp. And I suggest you go ahead and go through at least the founding of some of this algebra, but it is just algebra at the end of the day, so throw it into a solver. It's okay. Just say which solver you put it into. I, like a fool, did this out on paper. So, don't be me. Alright, so that's it. Kind of a shorter lecture today. We've had a couple of doozies lately, so I don't want to overdo it with you guys. Next week, we are looking at the midterm. So, I will post information about that, and make it available to you. The plan is for you to be able to have the week to take the exam, and then after that we're going to look at RL, RC, and RLC circuits, which kind of relies on everything we just learned to really get, and I think this is something that especially the mechanicals are really going to need later on. So, that's it. Great job. Go take a break, go hydrate, play some video games, I don't know, but have a great day. Good job. Talk to you later. Bye-bye!